Alrighty, we are on and rolling. Alright, so continuing with projectile motion, we are now looking at motion in 2D, specifically looking at displacement. So objects on a plane need not travel in a line like a hockey puck would. Finding displacement is a vector sum of steps. Perpendicular components are added independently. So we're looking at all of these things together. Once again, textbook, not the one we're using. One for uni. You could probably find it online if you want to read into it a bit more. But yes, these are what some of the more detailed and difficult vector diagrams look like. Each point, you have axis paths or vector paths for them as well. You can calculate that. Alright, so this is not appropriate for your age level. So we're going to skip that part and go here. So objects that move through the air under the influence of Earth's gravity undergo projectile motion. You know this. The acceleration is constant, both magnitude and direction. Examples include golf balls, footies, bullets, mortar shells. Anything you kick or hit goes pew is projectile motion. Okay? Simple as that. So we decompose the velocity vectors into two components to simplify projectile motion problems. Projectile motion problems. For example, a ball falling off a cliff initially moves horizontally and then begins to accelerate downwards to gravity. We neglect air resistance. Do not worry about air resistance. When it comes to projectile motion, it's up. We do not worry about it. It is kaput, not needed. Okay? So ball starts going out, and then gravity acts on it and it goes. Okay? Acceleration is gravity and it's downwards. Okay? And at each point of the fall, we can draw a vector for it. Okay? So, first rule, the horizontal motion is independent of the vertical. You have those two equations, v of sine theta and v of cos theta. Okay? So horizontal and vertical components of velocity are treated independently. We can do this with the components of any vector. Okay? You can treat them as individual things. Okay? So considering the velocity vector, you have the vertical fall and the horizontal movement across. The acceleration looks complicated, but look at the components of it. Okay? It's now less complicated when you look at it. Okay? Horizontal projection stays the same. The horizontal vector stays the same distance across all these parts here. The vertical velocity changes, it gets longer. Okay, only the vertical component is undergoing acceleration. And remember, air resistance is neglected. Do not worry about it. Okay? Right. So solve the vertical and horizontal of equations of motion independently. Okay? So with vertical motion has a constant acceleration. The position is given as this. We are using y here because we're going along the y-axis. Is the velocity at the original y origin point times by time divided by half. Wow. The y displacement is equal to the velocity at its original spot, the original velocity that it has at the y point, times by time, plus a half times gravity times by times squared, multiplied by time squared. Okay, that's the position. To get the velocity, Vy is equal to Vy naught plus Gt. Okay, horizontal motion has zero acceleration, so you cannot use these equations to calculate horizontal motion. The position is given as this. Displacement is equal to displacement across the x-axis is given as vxt or vx naught t, same as vxt. So velocity is constant because it's going across. There's no gravity acting upon the horizontal vector. It's just across at a constant rate because the arrows across are the same size, therefore it is constant. Right? because that's constant, no acceleration is being acted upon it. Alright, so we solve for each component separately, then combine the results when we are done. So horizontal, vertical combined gives us the angle here. Following through, you see the same is true for all. That's how we get the nice curve motion. So adding the vertical and horizontal velocity components at each point recovers the full velocity vector. So we have one part, two part, and then we get the third part, the full part, when you do it together. Okay, so an example of projectile motion. Consider a motorcycle driving off a 50-meter cliff at 100 kilometers per hour. How far from the cliff does it crash, neglecting air resistance? Okay, so reference frame. Origin at the top of the cliff, up here. This means that x0 and equals y0, which equals 0. That is 0. Y is positive upwards. This means acceleration is negative, so it's going downwards. Okay? So it's a negative 9.8. Right? Horizontal composition, well, horizontal component of motion obeys this law. Da, 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 da. Okay? So x naught equals 0 and a of x equals 0 because there is no acceleration acting on the horizontal component. So v of x remains constant at 100 kilometers per hour or 27.8 meters per second squared. You should know how to convert between kilometers per hour into meters per second squared. You should remember how to do that. If not, I will send you the year 11 textbook, which has the equation you need to know how to do. The distance traveled at this is horizontal velocity multiplied by time in the air, t. We don't know what t is, though. Oh no! So, we can figure out what t is eventually. So the horizontal motion ends at the same time as the vertical. So the going across ends at the same time as it going down because it's sorry. It is going across and down at the same rate, which means when it lands, both vectors or both motions stop. It's kaput. So we can find t by using the equation for the vertical motion because we know what acceleration is, we know what y0 is, we know what v0 is. Okay, so the initial vertical velocity is 0 at y equals 0, and a of y is gravity. So the equation becomes y equals negative half gt squared. Okay, this is 0, so kaput. This is 0, kaput. Therefore, you're left with this because gravity is negative. We stick a little negative sign, we stick a minus there. Okay, so we know at the bottom y is negative 50 meters because you're going down 50 meters. So we invert the equation to solve for t. Once again, you should know how to rearrange equations to get them to what they need to look like. So we have t equals the square root of negative 2y over g. Okay, which when you punch your numbers, you get this. Negative 2 outside of negative 50 times those together, divided by that, gives you this 3.19 seconds. Okay, once again, do not forget to write your units. Eddie. Next, now that we know our time and we know what v of x is, we find out how far the bike travels horizontally. So distance is equal to times multiplied by speed, which is that. And next question, what is the magnitude of the velocity vector, the speed, on impact? So first find the vertical component on velocity on impact. We have this. Okay, v equals negative gt, which is negative 9.18 times by the time, gives you that. So velocity is down, so it is negative. Make sure it is negative because we're going kaboosh. Okay, so we know the horizontal velocity is 27.8 meters per second. So to get the magnitude of the velocity vector upon impact, use Pythagoras. So we have horizontal and vertical. We're trying to find the diagonal. Use Pythagoras. Vx squared plus vy squared equals v squared, which is what this here is. There it is. This is, so we can work that out. So at impact, the guy driving the motorbike is going at 150 kilometers per hour. And finally, we can find the direction of the motorcycle at impact from using trig, where we use tan theta because we have the opposite, the opposite and the adjacent. Oh my word! We have the adjacent and the opposite. We can find this angle here, right? V of x, V of y over V of x gives us that, and that is the angle down here that this dude jumped off the I cannot speak. That is the angle in which the guy on the motorbike fell off the motorbike, and that is the angle downwards from his crash. Right, so key points. What kinematics are? We covered this last time. The significance of reference frame and coordinate systems. Difference between displacement and position. Blah blah blah. I don't need to read this. You guys have eyes, and you also have this PowerPoint. Okay, so we will leave this here. We will start dynamics next time. Okay, so I'm going to stop both of this. So this is the safe outline. Based on what we have covered in the last two videos, we have gone over this. Yeah, we've gone over this here. We've touched on this. We will go. Oh, no. Yeah, we'll go into detail into Earth's gravitational constant a little later. Motion formula we've done. Okay, all these things that say calculate, those are going to be in the questions that we are going to do this week in class, starting from Thursday. And also, so I have the questions from the lecture series online already on Daymap. I will put the questions from the textbook from SASTA on this topic also up on Daymap, and we'll go through them and examples together either at the end of the double lesson or on Thursday's single lesson. We'll see how we go. Alright, once again, if you guys have any questions, email me, ask me in class, whatever, and I will see you later. Bye!